All right, here we are in College Algebra, Chapter 3, Section 2, where we're going to talk about polynomial functions and their graphs. First, let's have a look at a very generic version of a polynomial. This thing is almost not helpful, although it's correct. Here, let's zoom in a little bit. Here you've got hold still. Here you've got a leading coefficient, a sub n, and then next to it you have a variable x that's being raised to the power of n. Now, just because we're seeing this term which has an x to the nth power, and then to the right of it we're seeing another coefficient with another x that's being raised to the n minus first power, and so on, all the way down to the second term with an x squared and the first term with an x to the first and the 0th term. This tells me that there are a lot of terms. There aren't always that many terms. Okay, this is just the generic structure for a polynomial. So don't worry about this thing. Worry about the fact that I can't stay on the right page. Take me back to the beginning. Sorry about that. Okay, and when we graph these polynomial functions of degree n, right, so the largest exponent present is going to tell us the degree of the function. That should be in your notes. The degree of the function is determined by the largest exponent. The number that's in front of the variable to the largest power is called the leading coefficient. And polynomials of degree 2 or higher have graphs that are smooth and continuous. They're smooth because they don't come to any sharp corners like the absolute value graph, which really looks like a V. And they're continuous because you could, theoretically, if you had an infinitely wide piece of paper, draw the entire graph without lifting your pencil off of the paper. On the left, we're seeing some examples of polynomials. This first one maybe is a 3rd degree polynomial. This one is perhaps a 4th degree polynomial. Comes out looking like a W. The graphs on the right are definitely not the graphs of polynomials because the first one has a discontinuity. It has maybe a jump discontinuity, you could call it. And the second graph on the right there has a couple of sharp corners, and that just won't happen when we graph a polynomial. There are a lot of little subtopics that we're going to see in this section, so you're going to be accumulating a lot of little sort of definitions or things to look out for. The next one is called end behavior, and the end behavior is what the graph does really far out to the left in the negative direction, and what it does really far out to the right in the positive direction. And when I say what it does, I mean, do the y values continue increasing or decreasing as you go really far to the left or to the right? And we're going to see some examples of that. Well, let's just look at these examples that we have right here. The end behavior of this leftmost graph, as it goes off to the left, as it goes off to the left, that graph continues to go in the downward direction. So you might say that it falls to the left. That same graph also looks like it's going to continue rising as it moves off to the right, so you might say that it rises right. The next graph over rises left and rises as it goes off to the right. So these are just, those are all the possibilities that you're going to run into for end behavior. It's either going to rise left or fall left, or it's going to rise right or fall right. That sounds confusing, more confusing than it really is. But that's what we're talking about when we talk about end behavior. How are we supposed to know the end behavior of a function just by looking at the equation? There is a really nice easy way to tell the end behavior. And we determine it by looking at the leading coefficient and the degree of the polynomial. And here are some examples. I don't love these examples, although they're true. I don't love these examples because I have no idea what these graphs are. I don't know. I've never seen these before. I'd much rather use a graph that I'm familiar with. So let me see if I can find... I'm just going to do some of my own work on the right-hand side of the screen here in order to at least give you another idea of how you can remember end behavior. Can you imagine the graph of y equals x to the first power? Y equals, we could even say y equals 2x to the first power. And do you know what that graph looks like? Well, you should be able to figure it out, even if it doesn't jump right to your mind, because it's of the form y equals mx plus b, which is slope-intercept form. There's no b value, which means it has a y-intercept of 0. It passes through the origin. And it has a slope of 2. And I said y equals mx plus b, which means it's going to be a line. And it's going to have a steepness of 2, a slope of 2, so it doesn't cut right through the middle of the first and third quadrant, but it's going to look something like this. And wouldn't you say that that graph falls to the left and rises to the right? I think we can agree. What about this equation? Y equals negative 2x. The only thing that's different is the leading coefficient is now negative. And that changes the slope, which you know means it's going to be looking something like this. And wouldn't you say that this graph rises to the left and falls to the right? I think you would. Can we also agree that because both of these equations have x to the first power as their largest exponent, that we can classify both of these equations as first-degree polynomials? Exponent is 1, first degree. So the first equation and graph that I drew here has a positive leading coefficient, and the polynomial is to the first degree. 1 is an odd number, so it is an odd degree polynomial. Again, positive leading coefficient, odd degree polynomial. And you'll notice that it falls left and rises right. Good news. Every odd degree polynomial with a positive leading coefficient, just like this super simple graph, they're all going to fall left and rise right. All of them. Just like this one. Just like this one. I can tell from looking at that graph. It falls to the left and rises to the right. Therefore, it must have been the result of graphing a polynomial of odd degree with a positive leading coefficient. I don't even know what the polynomial was, but at least I know those two characteristics about the original polynomial. Okay, so these two examples they were both degree 1. In other words, odd degree. Let's look at another pair. How about the equation y equals 3x squared? I'm choosing the number 3 arbitrarily, okay? But the x squared I'm choosing very specifically. Do we know what this graph looks like? You should. It's a parabola. It passes through the origin. And that 3 out front makes it look kind of skinny. It gets tall quite quickly as we go out in either direction. Tell me about the leading coefficient. Is it positive or negative? tell me about the degree of this polynomial. What's the largest exponent? Therefore, the degree is even. So this is an even degree polynomial with a positive leading coefficient. It rises left and rises right. Every polynomial of even degree with a positive leading coefficient rises left and rises right. And I'm going to put a negative sign in front of this now. You can imagine what's going to happen. It's going to reflect over the x-axis. Still pretty skinny, but concave down. Even degree, negative leading coefficient, falls left, falls right. These are the only 4 options for end behavior. And it doesn't matter how long of a polynomial you've got, in order to determine the end behavior, the only thing you have to look at is the first term, or if they've been shuffled around, you better find the term with the largest exponent. That's the one that we need to examine in order to draw conclusions about end behavior. So let's draw some conclusions about the end behavior of this function in example number 2. What is the degree of the polynomial as a whole? The answer is 3 because the largest exponent is 3. So this is a polynomial of degree 3. It has 4 terms, right? Terms are things that are either being added or subtracted. So it's 4 terms. If it had 2 terms, it would be a binomial. If it had 3 terms, it would be a trinomial. Once it's got 4 or more, it becomes a polynomial. Poly just meaning many. So it's a polynomial, degree 3, negative leading coefficient. Can't write with the eraser. There we go. Negative leading coefficient. Odd degree. Negative and odd. Negative and odd. There it is. Negative leading coefficient. Odd degree polynomial. Therefore, this function is going to exhibit the same end behavior, which is rises left and falls right. That's pretty easy. I think it is. The idea is simple anyway. It's just a pattern that you have to commit to memory. And I think that if you relate it back to graphs that you're already familiar with, that will hopefully help you remember them better. Okay, the next subtopic is zeros of polynomial functions. What's a zero? A zero is an x value that when you plug it into your function returns a y value of 0. So could the number 5 be a 0 of a function? Absolutely. If f of 5 equals 0, then 5 is a 0 of that function. Those x values are sometimes called roots or solutions of the function when it's set equal to 0. Don't get too hung up on roots, solutions, zeros. You can kind of put them all in the same family. Just realize that they're all about the function equaling 0. Okay? Whether the 0 of your function is a nice number like 5 or a not nice number like -2 plus or minus the square root of 5, we've seen x-intercepts like that before. But regardless of whether it's a nice number or not that causes your function to equal 0, those x values, nice or not nice, will show up graphically as an x-intercept because they cause a y value of 0. That's how we find x-intercepts, by setting y equal to 0. And then there's the multiplicity of a 0. So there's a function that they gave you here, and I don't love it, so I wrote down this other function in blue down here. And I thought that we could go through and talk about the zeros and the multiplicity of the zeros present in this other function g of x. G of x is, or has already been factored. I just made this function up and I wrote it out in its already factored form. You've got x plus 1 to the first power, x minus 3 to the second power, and x plus 1/2 to the fifth power. What, for starters, are the zeros of this function? In other words, what x values could I plug in for x that would cause the whole thing to equal 0? There are 3 different numbers. If I plug a -1 into this location, -1 plus 1 makes 0. 0 times I don't care what will definitely equal 0. Okay, so -1 is our first 0. If I plug in a +3 here, that will cause everything to equal 0. And if I plug in an x value of -1/2, that will also cause the whole function to equal 0. So those are our 3 zeros. Now, what are the multiplicity, or what is the multiplicity of each of those zeros? The multiplicity is determined by the exponent on the factor from which the 0 came. In other words, if we just look at the image here, this is an exponent of 1 right here. So the multiplicity of this 0 is 1. This, however, this factor of x minus 3 has an exponent of 2. So we say that the 0 of 3 has multiplicity 2. And to the right of that, the 0 that is -1/2 has a multiplicity of 5. Now I didn't have a lot of space to work right there, so the presentation of that is not great. You should write that in some larger space in your notes to make sure that you have a good example with a clearly articulated relationship between each of the zeros and the multiplicity of each of those zeros. You're welcome to read this. Maybe it's helpful to some of you, maybe not. Sometimes this mathematical language gets too particular. Yes, okay, so in the example that they gave, 0, sorry, sometimes I put my hand down on the screen and it just starts moving around. This x value right here, if I plug 0 in there, the whole thing goes to 0. This x value right here, if I plug in a +2, the whole function goes to 0. So the zeros there for that function are 0 and +2. This exponent of 2 means that 0 has a multiplicity of 2. This exponent of 2 means that this 0 has a multiplicity of 2. Too many 2's. Why didn't they do one of those with an odd exponent and one of them with an even exponent? Right. So, excuse me. Multiplicity and x-intercepts. So we already know that the zeros, thankfully my microphone has a mute button on it, so if I have to clear my throat from talking into all these videos, I can mute when I have to clear. So fancy. Behind the scenes things that you don't need to know, right? So multiplicity and x-intercepts. We know that the zeros, real zeros, show up on a graph as x-intercepts. It turns out that the multiplicity of a zero tells us something about what happens at that x-intercept. There are two options. If the multiplicity of a zero is odd, then the graph will cross the x-axis at that x-intercept. If the multiplicity of a zero is even, then the graph will come down and touch the x-axis and then go back up. Or maybe it will come up from the bottom, touch the x-axis as that zero, and go back down. We're going to see examples of that. Before we see examples of that, I've got some space here. Y equals x squared. Let's even make it better. How about y equals x minus 4 squared? The graph of this, 1, 2, 3, 4, is a parabola. That looks like this. This function only has one zero. The x value of 4 would cause this equation to equal 0. So 4 is the only zero. What is the multiplicity of that zero? Say 2. 2. Very good. It's 2. Nice. So 4 has a multiplicity of 2. 2 is an even number, so the 0 of 4 has excuse me, even multiplicity. And look what happens here. Our graph just touches the x-axis at that point, but then stays above the x-axis. Interesting. What about y equals x minus 4 to the third? This graph, 1, 2, 3, 4, looks like this, more or less. What's the 0 of this function? Still positive 4. What's the multiplicity of that 0? Now it has a multiplicity of 3. So it has an odd multiplicity. And look what happens at the 0. The x-intercept, our graph is crossing the x-axis. So even multiplicity touches and goes back. Odd multiplicity crosses the x-axis. So if these are helpful to you, if these are illustrations where you're familiar with the parabola and you're a little bit familiar with the cubic, maybe these images will come back to your mind when you're trying to decide what happens at the x-intercept depending on the multiplicity of your 0 that you're looking at. All right, now we actually have to do some work. Find the zeros of the polynomial function blah 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 and give the multiplicity for each 0. And then does it cross or touch and turn around at each of those zeros? Okay, step number 1 for sure is we need to factor this thing. So let's do that. F of x equals, I see all three of those terms have a factor of x, so I'm going to take that out, which leaves me with x squared plus 4x plus 4. We've seen that expression recently. I think that was in the previous section video, 3.1. And then let's factor it further. Let's work our way down the page. It turns out that x squared plus 4x plus 4 factors into x plus 2 times x plus 2. So I've written it as x plus 2 quantity squared. Now let's have a look at this and determine what the zeros are. I'm going to sneak in here and put in a 0 to the left of this So what I'm doing now is setting y equal to 0 in order to find the x-intercepts. So from our original function down to here, we factored. From here to here, we factored. And now we're finding zeros. And the process of finding zeros looks just like the process of finding x-intercepts, which is really what we're finding. We're just doing it algebraically. Okay, and then this, we take the x plus 2, set it equal to 0, subtract 2 from both sides, x equals negative 2. Great, so these are the zeros. And what about the multiplicity of each zero? So these are zeros. And the multiplicity of this 0, look at the exponent on the original factor that it came from. It was x to the first power. So this has multiplicity of 1. And then the 0 that is x equals negative 2, that came from a factor that said x plus 2, and that factor had an exponent of 2. Therefore, the 0, negative 2, has a multiplicity of 2. Now the first 0, x equals 0, has a multiplicity of 1. So what's going to happen at the x-axis where x equals 0? It's an x-intercept, but are we going to cross the x-axis there or just touch and turn around? Because it's an odd multiplicity, our graph will cross the x-axis where x equals 0. This one, however, has an even multiplicity. So I'll say it touch and turn back. Can we talk about end behavior as long as we're here? We're so deep into this thing. Let's talk about end behavior. What is the degree of this polynomial? Look at the original polynomial. What's the degree? What's the largest exponent? 3. And what about the leading coefficient? What number is there in front of the x to the third? That looks like an invisible positive 1 to me. So, as an aside, end behavior it has a positive leading coefficient and odd degree, right, because the degree was 3. Positive leading coefficient, odd degree. That should look just like y equals x, or y equals 2x. And y equals 2x rises to the right and falls to the left. So that's what this thing should do. So, rise right and fall left. Nice, okay. The only thing I'm not going to do is, the y-intercept happens to be at 0 also. Take an x value of 0, plug it into the function. Go ahead. f of 0 equals 0 to the third power plus 4 times 0 squared plus 4 times 0. It's a whole bunch of nothing, okay? So x value goes in of 0, y value of 0 comes out. 0, 0, that's the origin. So our y-intercept is at a point where we also have an x-intercept. At x equals 0, we have an intercept. At x equals -2, we have an intercept. We know that our graph is going to fall to the left, and it's going to rise to the right, and it's going to touch and turn back where x equals -2. So if we're coming up from the depths here, let me actually scoot that over just a little. Yep. So there it is, falling to the left. It has come up toward the underside of the x-axis at -2. Because -2 has a multiplicity of 2, which is even, we know that the graph is going to touch there and go back where it came from. So it's bounced off the underside of the x-axis there. It's staying below the x-axis, and then we start approaching that x-intercept at x equals 0. Now that one has a multiplicity of 1, which means our graph's going to cross at that 0. So let's have this thing quick start curving up and cross there, and it just continues on rising to the right. So other than, you know, how maybe compressed this graph should be, or if it should be kind of stretched vertically or something, you know, maybe this curve really should have gone way down here and then come back up to cross and stayed in here or something. Other than minor details like that, this is the shape of this function. And we just graphed a third-degree polynomial by hand. That's kind of a big deal. You're kind of a big deal. You did that. Okay, I did that, but you're going to do it next time. Another subtopic within this section of this chapter, and it's called the intermediate value theorem. This is a topic that I cover with my elementary calculus and calculus 1 students. So this is a pretty legitimate little subtopic here. And what the intermediate value theorem says is, I've always used this analogy. If a submarine is going to fire a rocket, which they can do, a missile, okay, a submarine can launch a missile. But if it could launch it from underwater, so this missile leaves the submarine, that's water. That's the submarine. Here's the missile. It's launching out of here. Oh yeah. Right, there it goes. And the missile's going to travel like this, and I don't know where it's heading, but that's where it's going. If the missile launches from underwater, and it ends up hitting, oh, how sad it would be, unless they're bad guys. This is why I'm not an artist, okay? This is an airplane, believe it or not. It's going to hit this airplane that's in the air. So the missile has gone from underwater to hit an airplane that's in the air. Is it safe to say that at some point in the journey of this missile that it was like just breaking through the surface of the water? Right, at some point, like right here, wasn't the missile terrible? God, it's a disgrace. My father would be so disappointed that I can't draw for squat. Right, at some point, right there, it's crossing the surface of the water. That's what now I'm erasing all of this because it's embarrassing. Not that though. The the water can stay. The intermediate value theorem says that if you start below the x-axis and you end up above the x-axis, then at some point in time you must have crossed the x-axis. Or similarly, if you start out above it and you end below it, then at some point you must have crossed the x-axis. That's what the intermediate value theorem says. It doesn't always have to apply to the x-axis, but usually we're applying it to the x-axis because we're talking about zeros. So here's a much better diagram than my terrible missile launching from underwater out of a submarine. That is a thing, right? You can do that? Launch from underwater? If you can't, you should. It's pretty cool. In this graph, at the point where x equals a, we are below the x-axis. In this diagram, on this graph, at the point where x equals b, we are above the x-axis. Since we have those two pieces of information, and assuming that we're working with a polynomial which is smooth and continuous, the continuous part's particularly important there, at some point in time, somewhere, there must be an x-coordinate, like c that's listed in this graph. There must be an x-coordinate c where we're crossing the x-axis. If you start below and finish above, you must have crossed at some point. Yep, you can read all of that. I'll put it right here, and then you can pause, and then you can read, and then I'm going to keep going. Use the intermediate value theorem to determine if this polynomial has a 0, an x-intercept, between an x value of -2 and an x value of -3. Okay. Well, I'm going to draw a little graph over here. And here's -1, -2, and -3. And let's see what happens. I'm going to find f of -3 first. Yuck. That's 81 minus 27 minus 18 minus 18 again. All of those are divisible by 9. This is 9 nines, take away 3 nines, take away 2 nines, take away 2 nines. So I started with 9, and then I took away 3, 4, 5, 6, 7. So then I only have 2 nines left, which is 18. Okay, so at -3, 18, I can plot that point. I'm over on my graph, -3 going up 18. There we are. And then let's look at f of -2 equals 2, 4, 16 minus 8 minus 4, 8 again, and minus 12. I don't really care what this is. What I care is that it's for sure going to be a negative number. It's -20. No. It's -12, which is at -2, -12. There we are. So where x equals -3, we're above the x-axis. Where x equals -2, we're below the x-axis. If I draw my curve through there, for sure, at somewhere between -2 and -3, we have to cross the x-axis. So, is there a 0 between -2 and -3? Absolutely. That is the intermediate value theorem. And is there more? There's more. I don't know why this screen keeps going black like that occasionally. Turning points. Not entirely sure why that's happening. Let me pause for a second. All right, I unplugged the iPad, plugged it back in. We'll see if it holds up. Where were we? Right. So look at this graph down here with me for a second. Y equals x squared. How many turning points would you say that it has? Well, I would say that it's going down here, and then it's going up hold still, graph. And then it's going up here, so it must have made some kind of a turn there. So I would say that y equals x squared has one turning point. Here's the graph of x to the third plus 2x squared. It's on its way up here, and then it's going down here, and then it's going up here. So I'd say that's a turning point there and a turning point there. What I'm trying to illustrate is that if you have a second degree polynomial, there's no way that you're going to have two turning points. It's a parabola. You're only going to have one turning point. The next graph, y equals x to the third, is a third degree polynomial, and it has two turning points. It's never going to have three. It could have one. Could it have one? No, then it would be a parabola. So a cubic is going to have two turning points. In order to adhere to its end behavior, it's got to have two turning points. Because it has to either, well, you know, we talked about it already. What this text is telling us then, generally, is that a polynomial of degree n will have at most n minus 1 turning points, where the graph changes from being increasing to decreasing or vice versa. A strategy for graphing polynomial functions. We've done all of these things, I'm pretty sure, except for symmetry. So number 1 says, do the leading coefficient test to determine the end behavior. So generally speaking, that tells you what direction that we're going to go. And in the one that we did, right here, the very first thing that I did was I put an arrow pointing down here and an arrow pointing up here because we had talked about end behavior, starting out by just roughing in what direction you're going to be heading is not a bad idea. Okay, I won't keep going up and down to that graph. Number 2, find the x-intercepts by setting f of x equal to 0. We definitely did that. We had found our zeros. We also examined their multiplicity at each 0 in order to determine if the graph was going to touch and go back, or if the graph was going to cross at that 0. We didn't actually compute, we didn't write it down, the y-intercept, but we did just verbally plug in an x value of 0 into that function earlier. We plugged in a 0, and the output value, it turned out, was a 0. So that one had a y-intercept of 0. Then we could use symmetry in order to help us draw our graph. We talked about the axis of symmetry when we were graphing a parabola in our conversation about quadratics. So that was one way, and if you look at that part of that video, it was pretty early on, I believe. We were able to graph one additional point by using an already graphed point and then reflecting it over the axis of symmetry. I believe it went from 0, -1, folded over the axis of symmetry, which was x equaled -2, and then we ended up plotting the point at -4, -1 in orange, I think. Anyway, you can use symmetry in order to help you with your graph. And number 5, being mindful of the maximum number of turning points. At the very least, that'll help you draw a graph that is not in excess of the number of allowed turning points for that particular polynomial. And are we so fortunate as to have reached the end of that section? Absolutely not. However, this is another problem like the one that we did up above, and we're already 44 minutes in. So maybe the only thing that I'll do for you is this. I'll help you factor this. Out of the first 2 terms, I'm going to take an x squared. Out of the second 2 terms, I'm going to take a -4. So I've got x squared, leaving me with an x plus 1. Factor out the -4. And I get -4 times x plus 1. And then I factor again. And that gives me x squared minus 4 times x plus 1. And I can factor that even further and write it as x squared minus 4 is a difference of squares. So I can write this as x plus 2 times x minus 2 times x plus 1. Find your x-intercepts by setting this equal to 0. Find the zeros. Find the x-intercepts. Make note of the multiplicity of those zeros, so you know whether it's going to cross or touch and turn at those x-intercepts. Find your y-intercept by plugging in an x value of 0. Jot down a little note about end behavior. Is it an even or odd polynomial? Does it have a positive or negative leading coefficient? Those things alone are going to help you draw a really accurate graph of this thing. And then maybe just inspect the symmetry of it. Does it look like it's symmetric about the y-axis or some other axis? Does it look like it's symmetric about the origin? Maybe even go into desmos.com or use a graphing calculator and graph this thing using some technology so you can get a feel for what it really looks like and then compare that to your graph. That's going to be the best way for you to check your work instead of me working through the entire process also. I think that you can do it. If you use our previous problem as a model, go through the motions on that one, and then check your work with a grapher, you're going to be in good shape. And that, ladies and gentlemen, is the end of section 2. Whew. Thanks for hanging with me on that one. I look forward to seeing you in section 3. See you there.